Thank you very much. I feel very privileged to be a part of the today's presentation, and I wanted to heartily thanks for giving me this opportunity. Uh, I'm sure, I mean, it's because as a we are all industrialist. It's like our though my profile could say like, okay, fine, I've done this that, but when compared to you, I think I'll be nowhere because you're all research scholars and you are like heavy into the research. So I really feel privileged to share some of my experiences and thoughts in this forum so that you can take a lead over. So thank you very much. Uh, so I think I would do some justice today. So let me share my screen. Is it visible? Just to make a check.
Yes, ma'am, it's visible, ma'am.
My screen is visible.
Yes, ma'am, it is visible.
Uh, I mean, the full screen is visible, right?
Yes, ma'am, fully it is visible, ma'am.
Fine. Okay. Thank you.
Thank you,
So
ma'am.
let's, yeah. So just before starting, I just wanted to mention one thing. Uh, Basically, we are industrialists in the sense we are into an engineering consultant. Maybe I have two slides to just briefly explain about Tata Consulting Engineers because I come from Tata Consulting Engineers Limited and I'm the discipline head heading electrical department. And as mentioned, I'm responsible for the quality review and various engineering designs from power plants, industrials, smart cities, and so on. And right now, I'm involved in certain new technology projects. As you all must be knowing, now the era is moving towards the new technology. So we should keep moving towards the new technologies and keep abridged ourselves so that we can leverage our expertise. So, and one thing I just wanted to mention here is uh, we are not into the research. So maybe I would be, maybe if anybody is like, maybe if you think that maybe I would be speaking more in depth about the research oriented, please pardon me. I'll be here to give you an overview about the technologies and some case studies, of course, and of course, the outlook of a smart charging technology. So I would also like to hear from you if any one of you are involved in this kind of a smart charging and EV interface technologies, and if you can share your knowledge, it would be great. So let's start. So today's topic is on overview on EV grid interface and smart charging. Uh, First, I wanted to give a very brief overview about TCE, just to give an introduction about the Tata Consulting Engineers, and then let's move on into the topic of today, that is EV. Though the topic is about the EV grid interface and the smart charging, to give an intro, I wanted to start with the EV charging classification, a very brief intro about the charging classifications. Might be most of you might be aware, but it is only for the uh, people who are not into it and for the basics to understand the basics of EV charging. Then let us go into the EV charging standards and next to the EV grid interface, which is the topic for today, and then on the EV grid impact and some few case studies. Then finally into the EV smart charging. So about TCE, in brief, as I said, we are an engineering consultation firm. So we are not a product manufacturer. We are core engineering consulting firm. So we offer consultancy services in the sense we do design engineering, the complete design engineering for process plant. In the sense, process plant includes hydrocarbon and chemicals. So you name anything, oil and gas, refineries, petrochemicals, paper, food, anything in chemicals. So we are there. And then the steel, metal, and mining. Then comes the energy. So in energy, we are into power plant engineering and the nuclear power plant engineering as well. And in the power, it includes fossil fuel, that is the thermal power plant, hydropower plant, and renewable as well. And also we are into the T&D, that is transmission and distribution. Then we have a separate wing to take care of the infrastructure projects, that is water, wastewater, sewage treatment projects, then urban development, that is building a smart cities. And around, you might be aware, like there is a mission on smart cities and 100 smart cities are built upon on it. So we are involved in almost 15 smart cities. And next is buildings, facilities, and master plan, then industrial facilities, maritime services, urban transportation, and so on. And some of our key highlights are we have engineered around 80 gigawatt of power plants as on today. And 35 million square feet of engineering has been done. And 50,000 MLD water treatment plants we have engineered. And we are also into 3D plant engineering for chemical and even the power plant engineering. And the services include design engineering, as I was saying, it is a concept to commissioning engineering, project management, procurement services, construction management and safety. And also we are into advanced technologies. The advanced technologies, when it means the digitalization and digitization, which includes 3D, scanner, IoT. So this is all in brief about EC. And so we are also into the renewable portfolio. There also we are into conceptual stage to conceptual stage engineering execution and the post-project engineering. And till now we have engineered around 13 gigawatt of solar power plants, which could be which was ground mounted, floating solar. So floating solar is also one of the new technology which is being implemented, and some are in pilot and some are being implemented. Then rooftop and microgrids. If time permits, maybe if key personnel are there, I wanted to have a word on this microgrid, because we are trying to do special microgrid projects standalone for campuses. The campuses could be an engineering campus and hospitals and so on, a big campus which is spread across with multi buildings. So we are also developing microgrid for campuses like colleges and universities, and we already have done a pilot project in one of the very big campus in Karnataka. So now let's move on to EV charging classifications. So all must be aware, like because of this climate change, there is a Paris Agreement signed between various countries, and India also is a member of it. And accordingly, EV initiative was started around a decade back. And as per that, every nation who are into this initiative has to implement electric vehicle. That is, by 2030, we have to develop 30% of EV. So for that, EV charging is very important. So charging infrastructure is the core for a electric vehicle. So so let's see how about the charging classification. So the chargers are generally classified by its location, level, and type. So location, when I mean, it is whether it is the onboard charger or off-board charger. Onboard charger is only an AC, whereas the off-board charger would be an AC or a DC, and then the private and the public charger. Next comes this onboard charger. As I mentioned, the difference between onboard and off-board charger is in onboard charger, the charger is within the electric vehicle, and the AC supply is given to the charger, which is converted into a DC, and ultimately DC power is power to the battery, which powers the motor and runs the vehicle. On the other hand, off-board charger is the charger is outside. That is, the conversion is done outside through a EVSC. That is the electric vehicle supply equipment. So the AC supply is given to the charger, and the direct DC supply is given into the battery. And by default, any car would have an onboard charger. And as I mentioned, off-board charger is externally. So you can give to the car either a AC supply or a DC supply. And as per the power ratings, the chargers are classified into level 1, level 2, level 3, and in turn level 3 is classified into AC and DC. So level 1 is a simple charger, that is a home-based charger. You can even call as a AC plug socket. So these are generally a slow chargers because it takes around 12 to 15 hours to charge a high-range cars and 4 to 6 hours to charge a mid-range cars. And this is charged using a 230 volts normal socket with 15 amps, and the power rate.
Ma'am, sorry to interrupt you, ma'am. A
Yes.
participant is asking whether you can do it full screen, only the slide alone, because is it possible, ma'am?
So it is not full screen, is it?
It is full screen. Matlab, we can also see the next slide and that
Oh,
also.
I'm
Only.
sorry.
Okay.
That is why I asked actually
Okay.
whether. Just give me a moment.
Yes, ma'am. Sure, sure.
Yes, sir.
Just give me a moment, please.
Sure, ma'am. Sure.
How about now?
Yes, ma'am. Now it's full screen, ma'am.
When I go to the presenter view, I think you're not able to see. Just
Yes,
let
ma'am.
me know how is it now.
Yes, now it is coming along with the next slide.
Okay, fine. Okay,
Okay.
fine.
Okay. Thank you, ma'am.
I think it's fine right now,
Yes,
right?
ma'am.
Oh, thank you.
Thank
Please
you, ma'am.
inform me if any disturbance or
Yes,
interruption.
ma'am. Sure, ma'am. Sure, sure.
So yeah, so I left it in the power rating. So level 1 has a very low power rating because it is a single phase. So the power limitation is 3 kilowatt, and you can see uh, the various make of the cars over here on the right hand side, and the models, and the charging time which is required. You can even see the last three, which is the Tata, Hyundai, Tata Nexon, Hyundai Kona, and the MG ZS, which are the recent launched cars in India, and the timing which it would take for a level 1 charging. That is, the Tata Nexon takes around 8.5 hours, Hyundai takes 19 hours, and MG takes 20 hours. This is because we're charging in a 230 volts, wherein the power consumption is only 3 kilowatt. Whereas if you see the battery rating is around 30 kilowatt hour, and Hyundai case it is around 40, and MG is 44.5. So the next is level 2. It is a next level to the slow chargers, that is the level 1. In this case, it requires an installation of an electric vehicle supply equipment, and the voltage here would be 230 or 415 volts, and it would be up to 40 amps, and the power range would be 3.7 kilowatt to 22 kilowatt, and the charge time would be 2 to 6 hours. And here, see, in level 1 it can be charged either in a residence or in offices using a simple 230 volt socket, but here you need a EVSC. So the best places for the charging would be residential apartments, and you can see even this is even a small wall box kind of an EVSC are available nowadays, which we can even mount it in our normal residence wall. So, but it's only thing, the normal 230 volt socket is cheaper. This would add a cost to it. So we can use it in residential apartment, office, public parking areas, and commercial public outlets. The next comes the level 3 AC, that is a fast charging. So level 2 and level 1 are slow charges, and level 3 is a fast charger. So level 3 AC, it is also through a supply equipment, that is a separately mounted EVSC, and the current limitation here is 63 amps, and the power rating goes from 22 kilowatt to 43.5 kilowatt, and the charge time here is 2 to 3 hours. But here level 3 AC supports only buses. Generally it is only used in buses. Except very high-end cars like Tesla cars has level 3 AC. Otherwise, no other cars uses level 3 AC. But for cars, we can go into level 3 DC. That is the fast charging. So it is also obviously through EVSC. And here the difference is it delivers a high power DC directly into the EV battery. And the voltage range is 200 to 1000 volts. And the power range is 50 kilowatt to 250 kilowatts. And the charging time is 20 minutes to 90 minutes. This 20 minutes to 90 minutes is the, it is in Indian cars, it is almost 90 minutes. And there are some high-end vehicles such as BMW, Tesla, and Nissan, which can offer even less than 20 minutes or up to 20 minutes. So this is a small comparison of level 1 AC, level 2 AC, and other types. Typically, the users where level 1, where to adopt level 1, and where to adopt level 2 and level 3, and so on. So as I was mentioning, level 1 is generally used in residences, office parking, and commercial fleet, or in city roads, but there we use it for two-wheeler and three-wheeler. And level 2, we use it for multi-story large residential complexes and commercial areas such as parking lots, malls, dinings, and large offices, commercial fleet, and city roadways for cars. And level 3 is only for buses. And DC fast charging can be installed in malls, city roads, commercial fleets, highways, airports, bus depots, and bus terminals, and on all commercial areas. Now let's move on to the EV charging standards. So the EV charging standards are divided into two, like AC and DC. In AC, we have 4 types of charging standards. That is Bharat AC 001, Type 1, Type 2, and GB by T. Next, in DC, we have 5 categories: Bharat DC 001, CCS, CHAdeMO, GB by T, and Tesla. This Bharat AC 001 and Bharat DC 001 is a standalone Bharat chargers which are compatible only for, and it is available only, it is only meant for Indian applications, that is Indian based cars and Indian based chargers. So it can only support the Indian based chargers and the cars. And here it is Bharat AC 001, it is similar to a socket type charging. The only difference is it has 3 independent charging sockets such that the 3 vehicles can be charged simultaneously, and it has inbuilt protection features, that is overcurrent, earth fault, and the residual connective devices. And it can charge a 3-wheeler, 4-wheeler, and as of now, the very initially launched cars like Tata Tigor, Mahindra e-Verito, and E2O Plus cars, that is the 3 cars which was initially launched in India, only can support Bharat AC 001. The newly launched cars, that is Tata Nexon, Hyundai, and MG, which is yet to be launched, cannot support this Bharat AC 001. Next, GB by T, it is used in only China. It is a Chinese-based standard. Next, Type 1. Type 1 AC standard is generally used in, it's a North American standard, and it is used in North America, Australia, and Japan, and it will not be used in India. And Type 2. Type 2 is an European standard, and it is based on IEC 62196, and it is adopted in India, and almost all EV at present have adopted Type 2 standard across globe. All European countries, including India, Asia, and many other countries, leaving apart these 3 countries, all countries follow Type 2. So this is the configuration of a vehicle side connector, and this is the EVSE side connectors, wherein you can see the RYB, that is L1, L2, L3, 3 phases neutral, and the control sockets, and similarly on the EVSE type. Next, let's move on to the EV charging standards DC. So as I mentioned earlier, Bharat DC 001 is specifically for the Indian standard. It's specifically an Indian standard, and it supports only the DC. And the voltage here is 100 volts, 200 amps, and it is suitable for single vehicle charging at 48 volts. The limitation over here is it's only 48 volts. So that is the reason which it cannot be used for any other cars apart from these 3 cars. And the communication between the EVSE and the vehicle is CAN bus. Next is CCS. This CCS is a well-known, it is called a combined charging system. thus it is CCS, and it is a open, universal and international charging standard which is used across globe, except the very few countries like China, India, Pakistan, Bangladesh, Nepal, other charges. For if you have to charge AC, you need a separate socket and a separate connector. So in the car of the other charging standards, you will have two plug sockets, one for AC, one for DC. But in CCS, in the car, you can find only one socket which is suitable for DC. This down below is the down below is DC and the upper one is the AC. But the connector is two. That is, if you want a DC, you should go for a CCS, and if you want to charge for an AC, you should go with the type 2. So that is the unique feature of CCS, and the power range is wide, 50 kilowatt and 250 kilowatt. Higher ranges are also in implementation, and the communication between the EVSE and the vehicle is PLC. Next are the CHAdeMO. CHAdeMO is Japanese standards, and the voltage is 50 volts to 500 volts, and the kilowatt range up to 200 kilowatt, and it is suitable only for DC fast charging. And the communication between the EVSE and the vehicle is CAN bus, and it is suitable for all Japanese cars like Nissan, Mitsubishi, Toyota, and Honda. And GB by T, as I mentioned in AC, GB by T is also applicable for DC, and it is a Chinese standard which is used only for Chinese cars. Next is the Tesla, which is a special proprietary kind of a standard used for only Tesla cars. This is a snapshot of the various countries and the charges which they use for AC and the DC. So you can see here India. India uses for AC normal socket, that is the socket type is either type C, D, M, and which is nothing but our industrial socket. And case of a level 2, it uses a Bharat DC or type 2. So both type 2 and Bharat AC would be applicable for level 2. And case of a DC, it is level in Indian case level 2, it is Bharat AC 001 and the type 2, and as well as Bharat DC also is put under level 2 because of the charging time and the kilowatt rating. And level 3 is type 2 because it can even support till 43 kilowatt. And in DC, it is only CCS is acceptable in India, and CHAdeMO also it can be acceptable as per our Government of Indian guidelines, and there is a GOI regulations issued on where to what standards to follow and what are the charging requirements and so on. Next, we'll move on very brief details about the e-bus charging. So in a bus charging, unlike like a car wherein you can charge at office, home, or in a commercial places, bus can be charged either in a depot or on an end stop or along the route. For a bus depot on an end charging, generally the normal DC chargers are adopted, which is of CCS standard or GB by T standard. But along the route charging, that is, the buses can be charged on along the route in the sense on every bus stop. So that can be charged using a pantograph type chargers, and the pantograph type chargers are classified into again two types, that is bottom to top pantograph and inverted pantograph. Bottom to top pantograph is the mechanism is in the buses, and only the conductive part is in the charging station, whereas the inverted pantograph is on the reverse. And the kilowatt rating ranges from 150 kilowatt to 600 kilowatt. So this is again the snapshot of the various charging standards used for buses, and it is generally 415 volts, and the voltage is up to 1000 volts, and the charging types are either CCS or type 2 for, as I mentioned earlier, level 3 is used for buses, so that can be used for bus depots with the connector type 2. So this generally is used in this is actually an onboard chargers, and DC fast chargers and DC fast chargers are mainly used in main bus terminus and in the along the route charging. Okay, now let's move on to EV grid interface. Uh, how to, if any questions, can we move on to the final after session? Can we keep the QA session, or you need an interruption in between? Hello?
Ma'am,
Hello?
questions may be asked at the end.
Okay, fine. So let me move on. Okay. So before getting into the EV grid interface, I just wanted to bring on screen a snapshot of the EV charging. So right, this is the India's outlook as on date. That is, as on 2019, in India we have around only few charges, whereas you can compare the other countries. The charging numbers are, you can see China has more number of charges running into lakhs, and as well the New Zealand and Norway stands next, and United States, United Kingdom are tens of charges, whereas India is in the incipient stage. So thus we have a less number of charges, but there are steps being taken to increase the charging infrastructure. And similarly, the fast charger numbers are also at the moment less, but you can see in China it is in the lakhs. But moving on, this is the forecast of the cars, which is going to be, as on today it is 6 millions. In 2030, to meet the EV initiative of 30 by 30 percentage EV by 2030, it is expected that 157 millions of cars will be on the road, and by 2040 it is 745 millions of cars, and by 2050 it is 1000 and odd cars. And this is the estimated charges uh, to support the electric vehicle on the road. So public EV chargers would be around 2 millions, and the buses would be around 2 lakh and odd million, sorry, 2.5 lakhs, and of course the three wheelers would be so much. So moving on to 2030 and thereon, the number of EVs and the number of chargers are expected to increase. So when the EVs increases, and thereby the supporting EV charges need also to be increased, so what happens? The electricity demand required also increases. So we can see over here, this is the electricity demand which is required in 2030. So you can see in India, it is almost a 400 gigawatt is the power demand which is expected by 2030. And in China, it is almost 1200. And we can see the scale, on the timing scale, the demand varies. And this is because generally the charging tendency is during morning time, because it is said that through a study it is stated that 80% of the charging takes place at home and or office, and the remaining 20% at the commercial places. So you can see this 6 to 9 is the peak, in all the countries where the charging demand is more. The off peak is in maybe after 10 or early morning hours are the off peak hours. And you can see in evening charging case, it is expected that the EV demand further add to the existing case, that is further a 20 gigawatt could be added in the evening case, and China around 60 gigawatt would be added. So all these things put together would increase a burden on the load pattern. So the peak loading is observed in evening hours during summer months, and you can see in this graph that the peak is during the evening hours. The evening hour is the peak, and that would and the worst peak would be in the summer months. So what is the impact? Because years to go on, when the charges keep, as of now, we are in a very incipient stage, and the amount of charges is insignificant, and the load which is being put on the grid is insignificant. But when we move on to achieve the target, the load is going to day by day increase. So what is the impact on the grid? So let's take a small, a very sketchy calculation that a car with a battery capacity of a 30 kilowatt hour, that is like our normal Tata Nexon cars, can charging 60% every day, consumes 18 kilowatt per day. That is 1.5 times the daily consumption. In some 1.5 the daily consumption, in the sense in summer generally residents would consume 10 to 12 kilowatt hour a day. So a single car is going to consume 1.5 times the daily consumption. So if we take a distribution transformer of a locality, say a 500 kVA transformer distributing a power to 80 houses, and if 20% of the houses add EV, and through level 1 charger it is charged, the load will increase to around 60 kVA, which is around 12%. So here you can see here, in a normal conventional car, 2 minutes it would take to fill the tank, and it can run on a 800 kilometer. And whereas in electric cars, it would take 20 minutes, 400 kilometers, and the 30 charging points is going to consume around 6 megawatt. So the 6 megawatt load is going to come on the grid. And this is the pattern at which each and every electric vehicles is going to load our grid. The timing pattern, it's generally, you can see the evening hours, the peak, the evening peak is high, and morning peak also is the high, and afternoon it is low peak. So what does it cause? The increase in the current in the power lines, and the voltage drop increases, and there is a loss in the transformers and lines, and the power factor deteriorates, and the total voltage drop in the network deteriorates in the peak hours. So this necessitates a high active power demand on the generating stations, and in a snapshot, these are the effects of EV integration onto the grid when the percentage of the EV increases on the grid. That is, the harmonics could occur, Saxwell, voltage imbalance, and transformer overload. And I wanted to present a few case studies. This is one of the case study which was performed. This is available in the open forum. This is a case study performed to find out the effect on the Indian distribution system done on a state-wise. So the case one taken was 90% of the four-wheelers are charged at home and 10% are charged at the charging station. As I was mentioned earlier, most of the charging takes place at home. And the case two is 70% of the four-wheelers are charged at home and 30% are charged at charging station. And the case three is a bit worse than case one and two. That is 50% are at home and 50% are at the charging station. Maybe worse with respect to the charging percentage, but this would work better. Case 4 is all non-commercial four-wheelers are charged at charging station and not at home. So we can see what the results. And this is the normal loading pattern without the EV. Without the EV, the normal loading pattern or 24 daily loading pattern, and this is for the Mumbai city. And we can see over here the peak is around it's 5.2 gigawatt, and in this 5.2 gigawatt peak is estimated in 2030, and as of now it is 3.6, and in 2025 it is estimated to become 4.5. Whereas over and above, if we add EV with based on the EV forecast, which is done in the year of 2025 and 2030, we can see over here, this is the load curve in a case of a case 1, where a 90% and 10% ratio, and this is the EV charging, I mean the EV load curve. Similarly, in case 2, this is the case, and case 3, this is the case 4 is the case. And we can see over here, the normal load curve is 5 point, I mean the demand is 5.2 in a case of 2030. The same, when EV is added, the case 1 load from 5.2, it is increased to 10.5. And similarly, case 2, it is 10.2. And the peak over here is 11.3. And peak over here is 15.5. So this is the scenario which is going to happen on when the EV is going to come on a full swing. Similarly, this is the case for Tamil Nadu, Chennai. So a similar case over here, but it is less impact because the number of EVs expected on Chennai on road is little less when compared to Mumbai. And of course, the loads are also led. Here it is around 4.8, but the same, the EV loads, you can see it is 8.9, which is almost doubled as the case previous. And as well as in case 2 also, it is 8.8. And in this case also, it is 8.6. So almost, in all the cases, it is doubled. So this is the snapshot. So we can see over here the 4 cities which has been compared in case of case 1, case 2, case 3, and case 4 in 2025 and 2030. So this is the percentage of the load. We can see over here the percentage load changes is drastic. In case 1, it is 35%, there is a change, and whereas in case 4, it is 58% in case of Delhi. And in 2030, it is 146%. So there is a total, because we have seen in the previous case, it is almost doubled. So the double case is in Mumbai. So 206%, there is a change. And in Chennai, you can see it's 100% increase. So this is going to create a high load stress. That is when the EVs are charged from the distribution grids. So the frequent connect and disconnect of EVs to the charging station having high power DC charges will generate serious power quality issues. And this is again a wonderful analysis which was done by our government of India through Ministry of Power. And this is the estimated public charging station curve, and this is the EV charge curve over the base load normal load pattern. And we can see over here, this is the minimum voltage profile without any EV. And the minimum voltage is around 0.9, that is 90%. Whereas with EV, the minimum percentage drops to below 85%. So you all know that all our electrical appliances are designed for plus or minus 10%, which would be plus or 90%. But here you can see it comes down at the evening time. It even comes down below 85%. So the transformer will be, every appliances may see this dip in the curve. So this is a bit severe, and we can even see the maximum drop. The maximum value also is not favorable. It is in the round of 96% around. So we can see over here, this is the bottleneck. So the evening hours are the time where it is getting overloaded. And that is the 6 a.m. to 12 p.m., the load is hardly anything. So the problem here is it is not actually it is time dependent, and a heavy load is imposed on late evening hours and the morning hours, and this creates a peak. So the load is not constant. It creates a peak at certain time. So what are the mitigation measures? So TOD, that is time of tariff, time of day. So the time-based tariff. This is one of the mitigation measures, and real time, that is the dynamic pricing, could be another one. And EV with renewable energy plus battery energy storage integration could be another mitigation measures, and then the smart charge. And this, and we can see one by one how it helps. So the mitigation measures are smart charging, which we will see in detail. Next is the TOD. So TOD in the sense, the low tariff during off-peak hours and high tariff during peak hours. So that what happens, the tendency of the people, the EV owners to charge on a low tariff time would be encouraged. And this is adopted in many countries, and even in India, we can see over here, Maharashtra, this is the Indian tariff guidelines. And in Maharashtra, Delhi, Telangana, and Uttar Pradesh, they have come out with the TOD and surcharge and rebate, and the surcharge during the peak hours and incentive when you charge during a low tariff. So this would definitely, it would lessen the peak load, because the peak load would be shifted to the low peak, that is the low tariff, that is the low demand hours, and thereby the peak would be curtailed. So this would be one of the great mitigation measures. Next is the dynamic price settings. Based on the real-time marginal cost of the energy, the dynamic price setting could be also achieved. And for this, we need a smart meters, wherein it monitors every time, every 15 minutes or every minute, it monitors the dynamic price setting, and accordingly, it will give an initiative to the charger to charge. So during low pricing, it will charge the car if it is plugged in, and during high peak hours, it will keep off. And this is implemented in Illinois. And EVs with battery energy storage integration also could be one of the mitigation measures. This is also being tried, and we have tried this in one of the city in India, and it is in the design, and we are doing one case study for one of the city in India, wherein EV with RE plus BESS integration is tried over there. So what happens when we integrate EV with battery energy storage, it could peak shave during peak loading, and it would in turn will mitigate the transformer overloading, and it can also help in the ancillary services like frequency regulation. So this is, so off peak you charge, off peak you charge the battery, and so that the load, the peak is curtailed. So let's move on to the interesting topic about smart charging. So we all must be wondering what is a smart charging and what it is going to bring to us in future. So I'm sure like everyone in India, or even I would say everyone in the world, are moving towards a sustainable environment, and I'm sure PSG also would be into it. And to create a more sustainable energy, renewable energy sources are most important. And for that, when EVs are integrated into the renewable energy, EV charging also need to be smart. So let's see what is a smart EV charging. What is a smart charging? Smart charging means adapting the charging cycle of the EVs to both the condition of the power system and the needs of the vehicle users. In the sense, it has to adapt both to the power system, that is to the grid, and the user's requirement. It should balance between the grid and the user's requirement. And in a charging system, the electric vehicle and the charging device share a data communication and makes an optimal use of energy, which is most important. Next, smart charging is a way of optimizing the charging process according to the distribution grid constraints, that is based on the grid difficulties and the constraints posed in the grid. The smart charging will automatically align its charging process, and local renewable energy availability, as well as the preferences of the drivers and the EVSE site host. And smart charging can be initiated either by the customers, that is the EV owners, or by the EVSE automated response to the, it can be either manually done by the local, that is the EV users, or it is automated through the automated response by the control signals that it is obtained from the grid based on the grid constraints and market situations, or based on both. So it is basically a cloud-based system wherein all EVs, all chargers, I mean all EVSEs are integrated to the grid. So what are the charging technologies in the smart charging? Now, as of now, the present technology is grid to vehicle. In the sense, grid charges the vehicle. So it is G2V. But the future or the technologies which is on the move, which is on the research is V2G, that is vehicle to grid, vehicle to L, V2L, and vehicle to vehicle, that is vehicle to two vehicles can speak to each other, then vehicle to home, and even vehicle to building. So as I was mentioning, right now what we have is a unidirectional control charging, that is grid to vehicle, or it is a V1G, that is vehicle is charged using the grid power. It is only a unidirectional. Whereas if you see in V2G, it is vehicle to grid. In the sense, it is a bidirectional. Bidirectional when we mean the grid charges the vehicle and the vehicle in turn can power to the grid. It can discharge the power to the grid based on the grid requirement. So it is bidirectional, grid to vehicle and vehicle to grid. Similarly, it is vehicle to home, vehicle to building. So vehicle will supply power to the home and it even power supply to the complete building. So you can see over here in V1G, the V1G is, it impacts the power system only during the charging. But in V2G, it is operable in both the regions, during charging and during discharging. So the current concepts of smart charging techniques are time of use. What are all the algorithms it uses and what are all the techniques it uses? Time of use pricing without automated control, then basic control, that is on off, then unidirectional control, bidirectional control, that is what we saw just before, V2G, V2H, V2B, and dynamic pricing with automated control. So we can see over here, because of all these automated controls and the smart charging technologies, it offers flexibility to the power systems. So as we move on through smart charging, the flexibility through the power system improves. So let's see how does this time of use price charging works. So we can see over here, this is the off peak, partial peak, and this is the peak. So when a vehicle to the grid is interfaced, the vehicle would charge during the off peak or a partial peak, and based on the response from the grid, the vehicle in fact would discharge during the peak. That is, the vehicle would help the grid to help in the meeting the peak demand. That is the peak shaving. Peak shaving is nothing but charging during the low peak and discharging during the peak times. So the vehicle, now the electric vehicle can help in the peak charging. So it is through the time of use pricing technologies. So these are the applications which was mentioned and the possible users as I was mentioning. So the time of use tariffs, it will be used for peak shaving and peak shaving with implicit demand response and a long-term grid capacity management. In the sense, short-term would be a peak shaving, that is we will be avoiding the peak demand, and in the long term it avoids transmission and distribution and even sometimes the grid capacity capacity addition. So these are the possible uses and the advantages of the smart charging curve. And the maturity level is high as of now, because it is on a pre-developmental it is in the developmental stage in abroad. And the on off during grid congestion management time, that is when there is a low frequency and or during any grid failure time, this on off can be automatically done. And then when we'll go directly into the bidirectional, not only it helps the peak shaving, it also helps during the it also helps to avoid the stress in the grid. That is, it avoids the it helps in frequency control, voltage control in the grid. That is, when there is a frequency control is required based on the grid signal, the all the electric vehicles would either charge or discharge. Thereby, it controls the frequency and as well as the voltage. And of course, this particular technology is in the testing stage. And V2H, V2B, similar kind to V2G, but in a smaller scale, because it is going to power only to the home and the building. That is, our vehicle will be powering our own home appliances. And this can be most used for the microgrid optimization. And this is also in a maturity level is medium, because it is in the advanced testing mode. And dynamic pricing, that is dynamic pricing, it is based on the dynamic pricing based on the cost of energy. And the users would be the load following and integration with the renewable energy. This maturity model is as of now low. So this is the smart charging services to power system. So we have already seen how peak shaving helps to flattening the peak demand, and it incentivizes the late morning and afternoon, and nighttime charging that could be adjusted during nighttime wind production. So during nighttime, the wind production would be more, so that can be supplemented during the nighttime charging. And as I was mentioning before, it helps in the real-time balancing of the grid by adjusting the EV charging levels to maintain a steady voltage and the frequency, and thus it helps in the distribution systems. And it also reduces the cost associated with reinforcing the electricity grid. And behind the meter, so it also helps behind the meter, that is for the consumer and the prosumer, that is the prosumer who produces supply. So it increases the self-consumption during of local produced renewable energy. If a house or office or a campus has a renewable, the self-consumption of the renewable can be increased by charging during the afternoon time and discharging during the peak hours. And it also lowers the dependence on the electricity grid. Thus, it can even help in the implementation of a microgrid. So with all these things, it helps the prosumers to reduce the energy bill by buying low cost energy and using it for the homes and avoid a huge tariff. So this, in short, like what are all the how it adds flexibility to a wholesale market, that is for peak shaving and for the transmission system operator. So this is only to explain like how smart charging helps in the complete portfolio, that is for the wholesale market, transmission system operator, it helps for the frequency control, and it helps for the other ancillary services, and for the distribution operator, it helps for the voltage regulation, and it also helps for the frequency and for the even the local congestion and the capacity management. And for the behind the meter for the consumers, it helps as a backup power, and even for the renewable energy increased rate of renewable energy consumption. And here is a small case study done. See, in UK, where 10 million EVs by 2035 is expected, evening peak demand would increase by 30 gigawatts with uncontrolled charging, but it would only increase by 0.5 gigawatt if charging is smart. So we can see the difference wherein the smart charging offers to the power system. A 2.5 gigawatt of power is being optimized. This is the behind the meter how it operates. So this is a vehicle to building wherein there is a meter for the distribution grid and the meter for the vehicles and the meter for the point of meter for the renewables. So based on the building consumption and based on the renewables and based on the grid disturbance. So the input from the building capacity constraints, that is based on the load pattern, and the inputs from the energy markets, that is the pricing tariffs, and even the response from the EV grid, that is if you want to peak shave or frequency regulation and so on, and input from the EV driver. I mean, even the drivers, because it is not that all the case like we have to support the EV. We should all, I mean, it is basically, it's like one EV driver is the priority. So based on the EV driver input and input from renewable energy, all these things will go as an input to the smart charging algorithm, which in turn would send a smart signal, that is to charge and discharge the car. So this is the behind the meter. So this is to show how a smart charging would change the pattern of a solar and a wind generation profiles. So this is with no smart charging. This is a solar, which everybody knows the peak is during 11 to the 4 to 5 hours in the afternoon time, and wind, the peak would be during the evening and the morning time. So using smart charging, we can see we are utilizing the solar power using the EV charging pattern, EV charging and the discharging pattern. So it coincides with the, so through this, the solar power consumption would be optimized, and same in case of the wind. So thus it helps both the solar and wind generation profile. So here it goes, smart charging versus normal charging. So of course, a smart charging with a cloud-based system can be scalable, interoperable, and it is fast, flexible, and of course it is future-proof. And we can see over here, this is a normal charging wherein the peak power is shooting up in many of the cases. Here it's totally shaved. And here the same, we can see for a vendor how it helps. All charging stations need to be from the same manufacturers in a case of a local smart charging. Whereas in a smart charging, it works with any combinations. And 20 to 25 to 40 stations are expected to be in a network. But here, any number can be connected to the network because it is a cloud-based system. And grid congestion local grid congestions, it can be avoided. But here, not only grid congestion, dynamic energy pricing, and renewable energy support, everything can be supported. And here, every few hundred meters, you need a charging station. But here, because everything is in a means of an app, so and everything is planned, so the dispenser of the charger need not be very close. And robustness, of course, because it is a totally it is a 24/7 communicated and through a cloud-based system with a self-healing system, so it is robust. This is the impact of smart charging on a grid. So this is a scenario wherein like 50% penetration in an isolated system with 20% solar share. With the uncontrolled charging, you can see the peak demand is increased by 9%, whereas in smart charging, it is only 5%. And here we can see over here, this is the smart charging pattern which was derived on a pilot case for various countries. And US, on a pilot case, when it has observed human normal charging, the increase in peak load is 11%, whereas in using smart charging, it is only 1.3%. Similarly, in Denmark, Germany, Norway, and Sweden, the uncontrolled charging was 20%, whereas in smart charging, it is -7. And the renewable energy curtailment without EVs was 10 to 23%, and the renewable energy curtailment with smart charging was 8 to 13%. And here the increase in peak load was 15% increase in peak load, but whereas here if you could see the reduction, that is the reduction is almost 43 to 50. So this is a snapshot of the complete benefit what we would achieve in future for smart charging interface with the grid. And again, this is a snapshot of the smart charging interface studied on a distribution grid. On a Hamburg's distribution grid, Hamburg is currently with the highest number of charging points in Germany, with with several hundred charging points in households and 810 public charging points. Load development analysis was carried out to identify the critical situation for uncontrolled charging of EVs with charging point loads of 11 kilowatt and 20 kilowatt. So they have used 11 kilowatt and 20 kilowatt, and two scenarios were studied. Scenario 1, a 3% EV share corresponding to 20,000 EVs loading in a private infrastructure will cause 200 bottlenecks. Next, a 9% EV shares corresponding to 60,000 loading in private infrastructure will cause a bottlenecks in 800 out of 6,000 feeders, and 15% of the feeders in a city distribution network would be of the bottleneck. And this, they estimated that this requires, because of this scenarios of this, because of this uncontrolled charging, the investment is required, which the scenario 2 would require a reinforcing approximately 10,000 kilometer of 0.4, that is a 400 volts cable, resulting in investment of at least 20 million euro. But the scenario was studied with smart chargers. So here you can see, this is the level of EV penetration in the grid, 5% and 15%. So 5% penetration was 550 million euro was the reinforcement cost estimated, whereas in a case of a smart charging, it has come half. It's 230. The same is the case with 15%, it is 1500 and 607. So this all these things because of the various technologies wherein the smart charging and a gamut of algorithms and the peak shaving, time of TOD, and what else, V2G, V1G, all combined, put together, automated, it acts to the grid response, and thus it avoids the grid reinforcement. Now we have seen enough about the how is the EV growth and how that EV growth is going to impact on the grid, and what are all the issues out of it, and what is the mitigation measures. And one such mitigation measure and one such is the smart charging, which is the future technology. And we have also seen the various smart charging technologies from V1G, V2G, V2L, V2B, and TOD, and what it is going to offer to the grid and the power system and the distribution system. Now let's quickly see the batteries for the smart charging. So most of you must be knowing the batteries are just a second. Yeah. So there are a wide range of batteries, starting from lead acid, which is an ancient battery, then nickel cadmium. The lead acid and nickel cadmium is ancient batteries which is used across, even at our home, industries, power plants, everywhere. Then comes the nickel metal halide and the lithium ion, which is the master of technology and the proven technology, and which is the hour of technology now. So you all must be heard of that lithium ion technology is the proven and the commercially viable technology which is being used in all the battery energy storage projects, as well as in the electric vehicle. So EV battery technology, capacity, and the technical characteristics determine the extent to which the cars support the renewable power integration and the smart charging. So the technical characteristics are as important, because all these what we speak cannot happen because the ultimately the battery is the one which is going to power the car. So the charge and discharge is going to take place through the battery. So the battery selection is very, very important, and its technology, capacity, and the characteristics are still a very key to the charging. Whatever, how much of a smart we go, the battery puts a bottleneck for any smartness or any. See, one more point which I wanted to bring here is, we all know that the charging time, which as of now the EV car takes, is around less than 20 minutes, and Indian cars are around 60 to 90 minutes. This is because it's not because of the charger technology has not improved. It's because of the battery. Because lots of advancements are taking place to improvise. But as of now, the technology is compatible only for the charge rate, is only compatible for a 20-minute charging. So that is why the battery plays a key vital role in the charging. And as I mentioned, the lithium-ion batteries has a very high specific energy and power, and a good cycle life, and lighter, and it's very reduced charging time. So that's why it has been used in all electric vehicles. And also then, but nevertheless, there are various ranges of battery technologies are in research, like lithium air, and you must be seeing we see a lot of technologies are on developmental stage. Lithium sulfur, then many cathode and anode materials are being developed and used, and they are used in even nanotechnologies, and even supercapacitors also are on the race. So as I was mentioning, the key characteristic features are end of life, that is the 70% of the battery life, and the depth of charging, that is DOD, the depth at which the battery can discharge, and the state of charge, that is the charge at which, I mean, it is actually the charge at which the battery can it is ready to charge, and the cyclic rate. The cyclic rate in the sense it's either 1C, 2C, or 0.5C. That is, in a 1 hour, how much power it can charge and discharge, which is called the cyclic rate. And battery degradation from increasing number of charge and discharge cycle has been a long debated issue with respect to the V2G. Why? Because it is see, the battery degradation and the battery life depends upon the number of cycles, and in a V2G the number of cycles could increase. So there is a issue with respect to that. So the battery degradation is affected mainly by the discharge current and the depth of discharge and the temperature of operation, which is more prevalent in V2G, because we don't know when the grid would charge and when it would discharge. So which affects the depth of which affects the battery duty cycle, and as well as the life, and it deteriorates. But recent tests have shown that the battery degradation with V2G is limited if the battery stays within a state of charge around 60 to 80%. In the sense, the charge state, that is the percentage of the charge with respect to the full charge, that is the state of charge, should be limited to 60%. So this is a snapshot or a comparison of the various technologies: lithium-ion, lead-acid, redox flow, and then Zebra batteries with respect to the applications. This is the renewable storage application. This is the ancillary storage applications. This is all with perspective to the EV, because EV helps in renewable storage, EV helps in ancillary services, and it also helps in the backup. And so we can see over here, lithium-ion, as of now, the technology which is used in EV is NCA technologies, that is NCA and NMC, that is lithium nickel manganese cobalt oxide and lithium nickel cobalt aluminum oxide. These are the two technologies which is widely used in cars. Next is the LFP technology, which is the iron phosphate. And even some cars, maybe like a Tesla, or very rarely cars are used with lithium titanic oxide. Actually, lithium titanic oxide has a very good specific energy, but it is very costly at the moment. So it is still on the research. But as of now, it is these two cars, these two batteries, NMC and NC, are widely used. And next is the LFP. You can see here. So this has more greens, which says that it is suitable for most of the applications. And I also wanted to just put on slide on the smart charging deployment, the projects, I mean the currently deployed projects and the projects which are on the pilot scale. So India is in a very incipient stage. Of course, we are not into, there are certain regulations set up for that, but we are not in the full swing. But you can see over other countries, they are in an advanced stage and there are already deployed projects and on a pilot scale. So the uncontrolled time of use tariffs is already implemented in China, Germany, Japan, UK, and US. And the basic control, that is on-off control, automatic controls, are already in place. And V1G, of course, in many of the countries. And V2G, there are a lot of pilot projects. V2G is in a pilot scale, is an advanced stage. And these are the already, you can see, operating pre-commercially, commercial operations. So EVGO and University of Delaware is, yes, it is already a commercial operation, and some of the others are in pre-commercial stages. And V2Hs are also, there are few technologies which is in Japan, which is in the pre-commercial stages. And dynamic pricing, as we saw earlier, it is still in the testing, I mean, it is still in the low testing stage. And not only on this, there is also research going on the second life of the battery. That is, after 70% of the battery which is being used in the EV, that can be used for other applications like battery energy storage projects or some other applications. So that is also in place. And these are the top car manufacturers who are into the V2G technologies. That is top OEMs, General Motors, Toyota, Hyundai, Ford. They are all in the V2G market. And this is the architecture of the smart charging. So you can see over here, EVSC. This is the smart charging algorithm, which talks to the EVSC, and it also talks to the transmission supply owner and the distribution. And this is the mobile app, which enables the charging, which enables the drivers to charge or discharge. And you can see this is the EV mobile app, mobile or the mobile, which is the communication between EVSE and the user interfaces, OCCP, and the data exchange between the central charging point operator and the smart charger would be OCPI. And this smart charger also communicates with the energy supplier. So it is the complete network interface between EVSC, charging point operator, then the operators, transmission operators and the distribution operators, as well as the renewable energy suppliers. Finally, of course, all technologies has its own challenges. So the challenges are EV infrastructure. So the smart charging requires a robust infrastructure. And in India, we are in an incipient stage. So the infrastructure is in the emerging stage, is in the phase 1. But Government of India is taking a lot of steps and has initiated lots of missions to focus on the EV infrastructure. Next, policies and the regulations. As we all saw, the tariffs and incentives should be on to support on the smart charging. There should be a total revisit on the policies and the regulations and the incentives. Next, the standardization and interoperability between EVs and EVSEs. Without this, the cloud automation and the total integration of the smart charging will not happen. So there should be total standardization and interoperability between the EVs and the EVSEs. Next, the electricity market design. I mean, the electric grid infrastructure also should be suitable for the smart charging, because we should have a handshake between the EVSE infrastructure and the electric grid infrastructure. So we are all moving towards, reducing the challenges, overcoming the challenges, and to move to a smart charging environment. So this is a snapshot of what we are today. So we are in a low penetration. By 2030, it is expected that we will move on to the high penetration, and 2050, of course. And now the batteries are in the range of 30 to 60, but 2030 it is expected to be 90 to 200, and even and it could go still further high. And we can see the parking times are almost 90%. It stands still. In 2030, it could be high, but it could be optimized. And most of the time, the charging takes place in home and office. In 30, it would be the same, but in 50, it would be the other way. And smart charging is in testing phase. Only TOU is common, but in 2030, it is expected that smart charging would be implemented, and there would be a huge market potential. And 2050, it would be a default. Smart charging would be a default and available to all. And finally, this is the evolution of EV flexibility. So from low penetration, we would be moving on to high penetration, and from fast charging of 150 kilowatt, we would be moving on to a high power charging, and individual owned cars will move to a reduced, the high parking time would be moving on to a reduced parking time, and uncontrolled charging would be moved on to a smart charging, which would offer a lot of flexibility in the grid and of stability in the grid and the flattening of power demand. And finally, this is a yes. So finally, we will see what is V2X. We all saw what is V2L, V2H, V2B, V2G. V2X is nothing but it is the future technology, which is V2 everything. That is, all V's will be interconnected. That is, vehicle to infrastructure, vehicle to network, vehicle to pedestrian, vehicle to vehicle. In the sense, you can see over here, vehicle to vehicle can speak to each other, and vehicle will speak to the signaling, and vehicle will speak to the infrastructure. That is the signaling and the traffic signals, and it will also speak to the pedestrian walks. So depending upon all this handshake between all the vehicles and the network, everything could be automated. So this is the future which is expected for us. And this is the outlook for a V2 grid outlook, which is expected, and India, we should be proud to see that India is also one among them. We have a very good potential, and I'm sure like most of you must be already on with many innovative projects. So I think you can gear up to do much more research and come out with bright ideas to make also in this smart charging environment. So that is all from my side. Thank you, one and all.
Ma'am, thank you, ma'am. Thank you for such an informative session. Ma'am, there are a few queries in the chat box.
Yeah, please.
You want me to read it for you, ma'am?
I think I should be able to read.
Okay, ma'am.
Hope I would have met partially your expectation.
You're very good, ma'am.
This environmental friendly batteries, as you all must be knowing, the causes of lithium ion. Actually, I think 3 to 4 years back, you might have seen everybody were like not a three, maybe a half a decade before. Lithium ion itself was in a threat. I mean, it could even cause a blast, and we have come out of it. But to come out with environment friendly batteries, there are, I think, research going on, and but we, maybe we could successful. But one thing which I want to, maybe it's in the other side, even hydrogen batteries, sorry, hydrogen vehicles, that would be the next era. Actually, lot of researches are going on hydrogen fuel cell vehicles. That is a vehicle uh, uh, fired by a hydrogen. So through electrolysis. Actually, there is a separate chapter for that. So that is the next era, and lots of researches are going on. And actually, we are also doing some case studies onto it. So maybe, but of course that is also not an environmental friendly, but that has much more, that I just wanted to tell about the next technology, because that is in a very full swing. Lots of researches are going on abroad and India, and we have lots of advantages over batteries. So otherwise it's all in the, maybe in the research stage. A base for predictions, it is all, see, the base is based on the iron up, the all my uh, data I have taken from the iron outlook. They actually come out with predictions and the future of EVs every year, which is based on the facts and figures, wherein all the countries, the members of the EV association formed, they are collecting the information, collating the information from all the members of the countries, and based on that, the figures are projected. I mean, it is based on the individual countries' projections, which is collated and uh, presented. Recycling of a battery, lithium ion, as you must be knowing, as of now, no. But researchers are showing that uh, there are many researchers going in, and they are in an advanced stage. I'm also eager to see that, because that would be a, because as of now, if you see, we have not crossed even, actually, maybe in abroad also lithium ion batteries, it may not reach 10 a decade, but as you all must be knowing, a battery life cycle would be around maximum 10 years. So I think this is maybe another 2 years, we could see a lot of batteries that requires a recycling, and it is hope and all hope that we would be, I mean, the researchers would be on what to say, we would get a better outcome on the researchers, and the batteries should be recycled. Yes, the number of charging cycles would definitely impact the performance of the battery, because the battery life is directly proportional on the charge and discharge cycle. But it is not direct, though it is directly proportional, it also depends upon on the depth of discharge or else the state of charge. So as I was mentioning, balancing between these two, we can optimize the charge cycle and the battery performance and the life cycle. Uh, I'm not getting what is the specification for RESS, BSS charging stations in India. Uh, I am not getting you exactly what do you mean by this, Kamlesh. Uh, it is basically, as I was telling you, in India, The charging stations, as of now, being implemented are all with CCS standards and the Bharat standard. For the Bharat standard, there is a specification which is released by Indian government. Government of India has released a Bharat standard specification, but of course that will be used only for minimum costs. But CCS is a open protocol with the European standard, and there is a standard specification available for it. That is with respect to the charging. And for the BSS, of course, it varies because BSS battery energy storage, it has to be done on a case-to-case basis. As I was mentioning, we are also doing some case studies on a case-to-case, like because it all depends upon the number of EVs at that area and what is the renewable energy and what would be the BSS. And one more important point is, as of now, the battery cost is high. It's almost half the price of the car. So over and above, if we go with an external BSS, it will not be cost effective at the junction. But it is expected that in future, battery cost is going to drastically come down. And 2030, by 2030, it is expected that battery energy storage cost is going to come 50% down. So definitely, EV with RE with BSS integration will play a very key role in future. I think I have yes, sizing of renewable energy storage and sizing of battery energy storage. Actually, that is a big subject as such. Maybe I think maybe I need another session to take care of the sizing because that is totally different. EV sizing we don't do it because it is all OEM. But for the renewable energy and the battery energy storage, we do it because we do a lot of battery energy storage projects, even for the grid scale capacity. I mean, for the megawatt scale capacity, we do battery energy storage projects. We have almost done half gigawatt battery energy storage projects. So that is all. I think I've answered most of the questions.
Ashchita.
It's better. 60% would be better.
Ashchita.
We can go even. I mean, theoretically, we can go till 20% depth of charging, but it is not advisable because the more the depth you go, as I was saying, the depletion of the cathode and anode will be more, and thus it's better to be 60% state of charge. Research, I'm sorry to tell you, it's like as such, say, we don't do a very detailed research, but we do a lot of white papers because as you said, there are individuals who are doing, who are working on active projects, live projects. But of course, as part of it, because as part of the technology, we also should do a case studies. We do a lot of case studies. So we have done a white paper on electric green mobility and as well as a white paper on hydrogen fuel cell vehicle. Maybe I can send you the link through Mr. Ashok. And it is available in open forum, both the white papers on electric vehicle and the hydrogen fuel cell vehicle that maybe can be used. And on a charging infrastructure, we have done certain case studies. That is how to develop a charging infrastructure for the city. What is the measures to take? How to size the how to size the, how to integrate to the grid. Such brief studies we have conducted. So anything else? Maybe you can also share some because I'm sure like great faculty members are there, are present here who are into researchers and even bright students who must be there. So you can share some thoughts which would be helpful for our yes. That is all from my side. And as I was mentioning, I wanted to discuss with some of the key members on a microgrid subject. Whoever online who is the key member, Mr. Ashok, if you're available, or somebody, if you could guide me like who will be the right person, it will be good for me, because this basically this microgrid projects we are concentrating basically on colleges first. And one good thing is we are involving students to, though it is a commercial project for us, but unlike other projects, we are involving students to be a part of this project. That is, we did one project in Karnataka, as I mentioned, wherein the final year students themselves were supporting us in the project for the field works. So this is something differently we have started now. So I wanted to have a discussion on this as well. That is all from my side. Next.
If there are no doubts from the participants, anybody would like to ask any doubts to ma'am? Ma'am, I think there are no more doubts. Thank you very much, ma'am, for readily accepting our invitation and for sharing your experience. It's very much needed for us because most of us are academics, so we do not have an idea of what exactly is going on in the industry point of view. So, recent research, recent things in case of batteries. So, thank you very much, ma'am, for sharing your expertise. I'm sure we'll also keep in touch in the future as you told about the microgrid project and other things. We'll definitely contact you, ma'am.
Yes, yes. It would be better like if you could give me the contact of your the key person wherein we
Yes.
wanted to be in touch, and
Sure, ma'am. Sure.
maybe our
Sure.
business development people wanted to keep in touch.
Okay, ma'am. Sure, ma'am.
Thank you. Thanks.
Thank you, ma'am. Thank you so much. So thank you participants for attending the afternoon session. Again, we'll meet tomorrow morning at 9 sharp at 9:45 for the next session using the same link. Thank you all.
I put my contact details over here. You
Yes,
can.
ma'am.
এই লিপস্টিকটা লাগবে না আগুন লিপস্টিকটা শীতে যে পড়েছে